So today I'm going to present my PhD defense, which is called Autonomous Driving System Rule Learning using Expert-Defined Causality. So before we dive into the problem, let's try to understand at a high level like how the autonomous vehicle work. So the autonomous vehicle, such as the one on the top right here, it needs to solve the motion planning problem, which is simply how can you drive in an uncontrolled environment. So it typically does that by decomposing the problems into 5 modules. And the focus of my thesis will be on the behavior planner, which I've highlighted here. So it starts with the mission planner. So the mission planner, you can imagine it knows its initial location and it has a destination that it needs to reach. So it's going to use a high definition map to determine a sequence of lane on which the vehicle is expected to drive. So it constructs a reference path that we will more or less follow. Then it gives that to the perception module, and the perception module responsibility would be to understand all of the static and dynamic features that are not included in the map, such as the vehicle, the pedestrian, but also the light signals that is controlling us. Then all this information is passed to the behavior planner, which in my thesis I decompose into 2 modules, a feature generator and a behavior selector. The feature generator responsibility is basically to augment the representation from the perception by adding a bunch of driving assumptions, such as, oh, I see those different locations where I can stop. I'm going to check based on what's the maximum deceleration rate of the vehicle, if I will be able to stop in time, or what would be the overshot if I were to stop there. Then when we have this rich feature representation, is given to the behavior selector, which considering this is going to set longitudinal and lateral objectives, such as when you reach that position, I want you to have that speed. So when we have those objectives, it's given to a local planner. The local planner is going to convert that into a trajectory. You can think about this as being an interpolation, such that we eventually, when we reach the position, we have the correct speed. And then when we have our trajectory, it's passed to a vehicle controller, we will transform it into vehicle concrete actions, such as control on the steering angle and pressure on the gas and brake pedal. All right, so this thesis assumes that we are working with a rule engine. So what is this? Well, it's a set of layers of rule. For each layers of rule, the rule are a set of if-then rule, for which it's constructed as if antecedent, then consequent. The antecedent is simply a conjunction of tests on human understandable features, such as if the traffic light is red, or if the time to collision with a vehicle is below a certain threshold. And the consequent is simply a driving behavior, which comprises a maneuver and a set of optional parameters, such as track speed at the speed limit of the road, or stop at this stop line, or stop now, which is unparameterized. So when the antecedent evaluates to true, it simply specify a candidate behavior, which is just an option that the vehicle can do. All right, so at a high level, how can we perform this? So imagine we are controlling this autonomous vehicle, which is on the left here, the orange car, and we want to reach the intersection, comply with the stop signal, and then perform a left turn. So this will be, there will be like a real-time update frequency, which depending on the chapter of my thesis will be in between 10 to 20 hertz. So depending on the speed of the vehicle, the distance between each measurement, each time that we capture the environment we are making decision are going to change over the time, depending on the distance that the vehicle is going to go. But what we will expect the vehicle to do is we will expect to see a contiguous sequence for which the vehicle is going to repeat track speed, track speed, track speed. And then at some point it will be close enough to the intersection, so it will switch to another contiguous sequence in which it will say stop at, stop at, stop at. And then at some point there will be a release condition, and it will create another contiguous sequence for which there will be track speed, track speed, track speed. So the system is designed such that the system can change its decision from maneuver to maneuver. So it can change its mind at any moment, and it will still be able to handle like a valid sequence of behavior. All right, so let's try to understand how each layers of rule work. So the first layers of rule, we are still the same orange vehicle here, is simply checking the environment and decide what it can do. So for example, there is a speed limit here, so it can say, oh, I can try to drive the speed limit. There is a blue vehicle here, so I can try to synchronize my speed with the blue vehicle, such that if it comes to a stop, I come to a stop. There is also a stop line here. We have a red light, so we might want to stop at that stop line. there is a white vehicle crossing, so I might want to stop on the physical area of the intersection, giving the right of way to the white vehicle. And similarly, there's a pedestrian crossing. I can stop before that. Now, if you just think about this before I go, at the end of this layer, we have a bunch of options, but they might be inconsistent in terms of maneuvers and parameter. But it's okay because we also have like a second and third layer. The responsibility of the second layer is simply to apply a precedence table. So the precedence table will simply create a total ordering over the maneuver. So it will say, I prefer to pass obstacle instead of yielding. I prefer to yield instead of stopping now, etc. So I say a total ordering. This is partially true because there is also a default behavior, which is simply if all of the rules in the system, all of the antecedent evaluates to false, then in such case we want to perform an immersion system. There is also a second goal to the second layer of rule, which is to define the set of implementable behavior. So in this case that we were studying, the behavior we will end up doing is the stop at behavior. So for the stop at behavior, it extracts the relevant parameter, so the parameters that are compatible with the stop at behavior, and for each parameter is going to go over the set of candidate behavior from the previous layer and is going to check what are the candidate value. So when we collect all of the candidate value, it passes that to the third layers of rule. So in the case of the stop at behavior, we have 3 candidate value for the stop location, which are depicted with the pink arrow, and 2 candidate value for the blue arrow. So the third layer just perform minimization over those parameters, so closest stopping distance and lowest speed of them all. So if we suppose the blue vehicle is actually complying with the stop signal, it's going to imitate the speed of the blue vehicle stopping behind him. So that's the idea of how we arrive to a final behavior. All right, so now that we know that, we can start thinking about the problems that I've been solving throughout my thesis. So the first one is, how can we learn a rule-based policy to control a specific autonomous vehicle that aim to drive in the real world? Now, there is challenge out of this because if you look on the internet, you won't be able to find a data set that fairly represents what your vehicle is capable of doing. So you won't find a data set that already have all the maneuver and all of everything labeled. The second thing is you can try to work with a simulator, but it won't necessarily fairly represent the specificity of your autonomous vehicle software stack. Another constraint that you have to consider is that testing in real condition is risky because there could be like accident and things like that, and it's also cost intensive. So we would like actually to convince yourself that the rule can practically control an autonomous vehicle. That's my first experiment. So how I've been doing this. So first of all, if you want to start driving, you will probably start with a driver handbook, which is the natural way that I've went as well. If you open the Ontario driver handbook or the Texas driver handbook, there will be a bunch of situations. And for those situations, there will also be a problem statement where they will explain a little bit what you are expected to do, such as when turning left, always yield the right of way to any vehicle coming straight through from the other direction. So if you read that, well, they already have identified what's the behavior here. They provide you some context, so the behavior is yield. They provide you some context here, so you wanted to turn left in that case here. And what you need to check, you have some information about the feature and you need to monitor, like the right of way to any vehicle coming straight, etc. So you can use the driver handbook to actually construct a training suite of example. So basically here it's a degenerated example. The vertical axis is feature A, the horizontal axis is feature B. Let's suppose there is only 2 features. So given the driver handbook, they will have identified some value for feature A and B for which the behavior is known. We call this a test cases. But there is also a bunch of white area here, so it's a valuation that is possible for A and B for which we don't know what the behavior needs to be. But this is nothing more than classic machine learning problems, so we can learn the rule and find boundary that match all of the correct decision here. So that's kind of our goal. So in our rule learning procedure, we start with the most generic rule as possible, which is if true, then a consequent. And when we update a rule, we can only add constraint to the antecedent of a rule, making it more specific. Consequence never going to change. So it's classic machine learning problem here. So our goal is to create a set of rules for which each rule could correctly identify as many test cases as possible, true positive, without mislabeling any test cases false positive. So you do that with confusion metrics, etc. So I'm not going to go over this, but the details are in the thesis. All right. So at the end of the process, you end up with a policy where everything will be properly classified for the test cases that are known. And one thing that I want to insist is that our problem is perfect for using separate and conquer, because our rule are having precedence. And if you think about it, if you start learning the rule that have the highest precedence, then after that you can take all of the test point that they are covering and then remove it completely from the problem, and then you can learn subsequent rules. So it's a perfect setup for applying those separate and conquer principle. All right, so when you have learned a policy with the driver handbook, at the end of the day, well, you still don't have a policy that have all of the specificity of your vehicle. So what I've been doing afterward is I've been learning also with a safety driver. I've been involving the safety driver. The safety driver is simply testing the policy, and then at some point maybe he feels that the situation is a little bit dangerous, or he's unpleased or uncomfortable, and he's taking over. So every time that he's taking over, we are going to record that and extract information out of this. So we can use visualization such as in the RViz software, and we can monitor the sequence that we have recorded, because we could record every run that we do, and we can inspect the rule engine decision using forward chaining and backward chaining to understand which rule trigger and which other rule did not trigger. And then we can have a discussion with the safety driver to discuss if it's really a misbehavior, and if it is, we can ask and come with an agreement with the safety driver about what we should have done differently. And when we identify that, because it's unpractical to do statistical learning from the real world, we also need to incorporate a sanitization procedure in which we are going to replace the stuff in RViz, but we are going to, for the sake of learning the rule, remove the stuff that were irrelevant. So even if there was a bunch of vehicle detected, we're going to parse that such as to provide as much as possible causal feature to the system, such as to avoid having to train for a long amount of time for reaching a decision. So at the end of the process, you still have new test cases, you incorporate to the test suite, and you use the same learning procedure as before. At the end, we were able to drive 110 kilometers on public roads on Waterloo and achieve 98% of autonomy, which at the time of this experiment, which I think was around 2018 here, we were having comparable performance with respect to state-of-the-art deep learning architecture. The information about human intervention provided in the thesis, not going to cover them right now. So let's switch to the next problem. So yes, okay, at this point we have a procedure to learn the rule for a specific autonomous vehicle, but it still doesn't tell you how to fine-tune those rules. How can you find the threshold? So namely, when can you say, I need to switch from one behavior to another? This is not something you will find on the driver handbook, and this is something that's going to be very costly if you do it in the real world. So here I'm going to incorporate in my procedure a simulator. So I'm going to start working with the Causality simulator, because here I'm going to work with requirement, and the Causality word challenge simply define a bunch of requirements for me. So here I'm assuming that the task of driving can be described as a set of qualitative and quantitative requirements. Requirements are simply statements such as, oh, the ego must not collide with a pedestrian. Ego is just another name for the autonomous vehicle. It could be also, ego must not be on the physical area of an intersection when the relevant traffic light is red. So they have statements like this, and we assume that the simulator will track the autonomous vehicle and be able to say, oh, here you have violated that requirement. So the simulator will provide that information. All right, so here we are assuming that at some point, the simulator is going to say from tx xv to tx xv plus t, you have violated a given requirement. So if you think about the natural way of what you need to do at that point, is we want to extract a labeling function. So the purpose of those adaptive search windows is exactly that. At a high level, you can imagine that you can provide to a human expert a video trace where the vehicle end up, for instance, having a collision, and ask the human expert, okay, what should we have done differently? So the human expert could simply pinpoint, okay, from there to there is a misbehavior, so it will identify a contiguous segment. Now, this step here is a little bit problematic, because if you ask that task to a human being, he won't be able to know exactly when the behavior should start, because, well, he cannot understand all of the dynamic of the world, etc. So we are going to relax this problem, Lily. We're going to relax this problem by simply asking, okay, just find me an optimistic contiguous sequence for which it's sure that here we need to perform that behavior. And when we have that, we are going to also have a search direction. And when we have a search direction, it simply say, if you were to cover, Lily, if you were to cover the full contiguous sequence with the correct behavior, and it still lead you to unmet requirement, then you will simply expand more and more on the search direction to actually be able to fine-tune where you should start to perform that behavior. Now, it's not enough to just have a contiguous sequence. You also need to provide a label with that contiguous sequence. This comes with a template rule. The way we were performing this is simply for each of the requirement, we are going to tie it with a template rule. And that template rule will simply say, okay, I'm going to define simply what's going to be the behavior that I want the vehicle to follow when we face that violation. And for the if statement, the antecedent that we are going to put, I was using a recommendation system that was simply using the contiguous sequence and extracting feature that was common over that contiguous sequence. So at the end of the day, we want in that contiguous sequence to have the label that we put in the template rule. All right, so given that, what we have been doing is we have been creating an experiment where our main goal was to try to learn in a single town. So in town 1, we have 10 routes. We will learn the policy out of those 10 routes, and we will see if we generalize to another town. So it's town 2 and I have 6 routes and have a similar operational design domain. We also, for the sake of comparison here, just going to compare with Interfuser, which is a top performer on this particular challenge, but he has been trained on town 2 as well. So the comparison is not going to be rigorous because, first of all, Interfuser can simply throw what he has learned in his training procedure. And second, we are not going to suffer from the exact same noise because Interfuser is going to solve the whole perception problem. In your case, we are just going to inject proportional Gaussian noise, which is the noise that Carlo used on for the location of the ego vehicles and so on. So the sake here is just to check that we have trained on town 1, and we can see that our procedure is able to generalize to a completely new town. So it's not rules that are just tied to a specific operational design domain. And the purpose of the comparison was just to check that we are not way behind the leading competitor. Okay, so after this experiment, the next thing, naturally, is to push this experiment further and make a fair comparison with our competitor, which I've done. So the purpose here is that if I'm performing similarly as a deep neural architecture, but I have a white box, then it gives incentive for using my system. So I'm going to put both systems into the same condition and check how they are going to work. The other things that I will do along the way is I will clarify how I can perform update when I'm extracting contiguous sequence so that it becomes clearer. All right, so suppose we have a system. Maybe this system has 1 billion of rules. It's not important, but at this point, when it's facing that particular scenario here, there are going to be only 3 rules for which the antecedent are going to evaluate to true. Those rules are R1 aim to track speed at the same speed as the leading vehicle, R2 aims to stop behind the leading vehicle, and R3 aims to creep forward to get closer to the vehicle. So those rules, they are interacting with each other, and here we are assuming that we have a collision at some point. That's going to be the violation being reported. So how can we address this problem? So if you think about the task that perform layers 2 and layers 3 is it create kind of like a total orderings over the rule. So here in this specific example, the ordering of the rule are defined by the maneuver. So pink, which was creep forward, is preferred over the stop hatch, which is preferred over the track speed. And suppose that for the violation that we have at XV, which is we collided with a vehicle, the solution will be to stop at. So what we do here is we start at the violation here and we go backward because we need to address a state before in which we had the misbehavior, and we look for the very first time where the antecedent of the template rule producing the blue here will be true. We identify this xj here, and then we continue going backward until the antecedent of this template rule is going to be false. When it's going to be false, it's going to define you a contiguous sequence, and you're going to simply say in that contiguous sequence I want everything to be blue here. So given that, the first natural thing is if you're able to find in that contiguous sequence some element on which there is no blue here, then in such case you simply want to insert the template rule because it will put blue everywhere. So that's the first step here, and now you end up with a sequence like this where blue is everywhere. But as I say, the rule has precedence and pink is preferred over blue. So the next thing that you're going to do is you're going to find where there is some pink here, and you're going to take that pink rule and apply the algorithm that perform generic to specific. This is the same algorithm that I've told you start with if true and then perform machine learning and change the value based on the different test cases. So this is going to eliminate the pink here, and then you end up having some blue everywhere here. But still, even if you have blue everywhere, it comes from an optimistic assumption. And that optimistic assumption, if you say, well, no later than that, I'm sure that I need to break at that point, it doesn't mean that you start breaking at the proper moment. In order to be able to break at the proper moment, you will not only consider the antecedent here, but you will consider the whole contiguous sequence of blue, and then you will expand on its left to add more and more of those test cases to start stopping sooner, and you will repeat the procedure until the violation at XV is eliminated. So that's kind of the idea. So we have been applying this procedure on the Causality leaderboard, which is a rich operational design domain which have country, freeway, highways, and urban road, a bunch of intersections, sometimes regulated by nothing, but sometimes regulated by stops or traffic lights. The shape and the size of intersection vary. Tunnel, bridge, roundabout, cul-de-sac. Sometimes, depending on the town and on the route, there is little to dense traffic, and the traffic may or may not comply with the traffic rule, so you can see vehicles that just decide to cross the red light. There is jaywalking, pedestrian, and bicycle, and you can have loss of control by driving on a debris on a high patch, something like that. What we will do here is we will basically take the whole architecture of Interfuser, which has a bunch of neural network, and what we're going to do is we're going to change the mission planner because we want to control like where, in which direction our vehicle is driving, and we are going to change the safety controller, which is just the thing that decides what the maneuver shall be. So for the rest, all of the perception and all of that, both systems are using the exact same thing. Our goal is to make the comparison as fair as possible. So the result kind of showed that I've been able to, like, I have mostly done 2 tests. So one of the tests was to drive in the same town as I've trained and to compare my performance with Interfuser based on a randomly generated route. And my other experiment here is I have performed the exact same thing, but on 2 towns that has been seen, and I've compared both performance. And in both cases, well, of course, when it's in the same ODD, we are actually performing a little better. So my performance decreased a little bit, but we are still beating Interfuser in both cases, which is good because at the beginning, I just wanted to have a performance that is similar, but it turns out that not only I can have a performance that is similar, but I can manage to beat a deep neural architecture while having a white box. I've performed some other experiment, but I'm sure I'm starting to run out of time, so I will go to my conclusion here. So the rule automatically provides an explanation of the decision, of their confusion when the decisions are bad. Human experts provide minimum causality for each of the requirements, but the causality of more complex interaction is learned by the algorithm that I've presented. The main limitation is, of course, there is a human effort involved for feature generation and also for labeling procedure, but we believe that this is inevitable and worthwhile. And at the end, the result is a simple, explainable policy that outperforms a leading competitor, and that policy is in my thesis.